Alrighty, that looks like an entire mountain of identities there, doesn't it? But turns out we already knew those. This is just the coordinate trig, where we have sine as y over r, cosine is x over r, and tangent is y over x, and then our secondary trig functions. So that's not new. But what we do need to see here is something that we had discussed earlier in the year, which is because the sine of A is the same thing as the cosine of B. Those are called cofunctions. And they're cofunctions because they're complementary angles. Complementary angles add up to 90 degrees. So that relationship always happens. Sine to cosine, cosine to sine. And then one that we probably didn't spend a lot of time talking about was tangent and cotangent for an angle. That those are going to be reciprocals of each other because we already knew that, knowing what we did about cotangent. So the cofunction idea is, if you have one, you should be able to find its cofunction. So what we see here is that the sine of pi over 2 minus theta, okay, wait a second, let's think in terms of pi, let's think in terms of radians, that's 90 degrees. Well, that makes sense, because if they have to add to 90 degrees, the sine of this angle should equal the cosine of this angle, so that works. And then we see that they go from cosine to sine, makes total sense, cofunctions, tangent to cotangent, cotangent to tangent. But then, like I said, a couple we really didn't investigate a whole lot would be secant and cosecant and cosecant and secant. And that's because we were more determined about the primary trig functions at that point than we were the secondary. But it makes perfect sense, since sine and cosine are cofunctions, that if you take their reciprocals, plop a 1 on top of them, secant and cosecant should have that same relationship. So those are going to be cofunction identities that we're going to use to try to simplify some of the, algebra that they give us involving the trig. Then we also need to keep track of odd versus even. And as we went through the graphing, this became really evident too, and that is that we really only have one of our three basic functions that's even. And when they're even, that means whatever we have on the x side of the axis is also on the y. And that's going to be cosine. Because when we graphed cosine, it did that. So cosine is even. And that means a negative in front of the x doesn't do anything to the graph. Here we have a positive x that's giving us this y value, and we have a negative x that's giving us the exact same y value. So a negative with the x doesn't matter, and that's why when we look at this, we see, hey, wait a minute, where'd the negative go on that? Well, it's even. So if it's even, we don't need the negative. Part of simplifying that will be taking it out. And if it works that way for cosine, then for secant, because it's the reciprocal, it's going to do the same thing. And in the others, notice it doesn't go away. We just move it to a new spot. That's all we do. And that's going to be, like I said, part of the simplifying. Trying to see, okay, do we have this as negative? Do we have this as positive? How is that going to work? So just remember, cosine is even, and then pretty obviously secant will be even because it's the reciprocal to cosine. So down here, using more identities. That's what we're supposed to do. We're going to be using lots of identities in lots of different ways today. And it says if the cosine of theta is 0.34, find the sine of theta minus pi over 2. Sine of theta minus pi over 2. Wait a minute. Isn't that supposed to say pi over 2 minus theta? Take a look at your identities up above. Wasn't it always 90 degrees minus theta? Well, we need to reverse that then. So to reverse it, we'd pull out a negative 1. So now the question is, does that negative 1 need to stay in this function? So I think for a second, well, it's cosine and secant that are even. Those are the ones where the negative can disappear. That's not what this is. So I'm just going to bring it out in front. So I can deal with it out there. Wait a minute. The sine of 90 degrees minus theta. Isn't that cosine? And didn't they tell us what cosine of theta is? And there it is. So what we're doing is we're starting to learn how to do proofs in trigonometry. I suppose I should say it a little louder. Trigonometric proofs. That's what we're learning to do. We're learning to take what we know and work logically and reason to another step. At this point, we had numbers to do that with. But eventually, we're going to get to the point where we're proving some trigonometric identities. So B says, using identities, simplify the expression to either 1 or negative 1, whichever it's supposed to be. And we have sine of x times cosecant of negative x. With cosecant, do we get to take the negative out of the picture? No, we don't, do we? So sine of x times negative cosecant of x, just putting that in front. Well, okay, but I might as well put it in front of the whole thing, because it's times, it's going to be negative, whatever it is. And now I start thinking about other identities that I know. And I think, wait a minute, cosecant. Cosecant is what you get when you flip sine, right? And I think of this in terms of fractions, and I realize that's all going to cancel out and give me a 1. The answer to that is negative 1. That's the answer to that. So using the identities and just reasoning through, okay, there's a negative. What do I do with the negatives? Can I get rid of it? Do I have to keep it? Where do I want to put it? What do I know about sine, and what do I know about cosecant that can help me as I go forward? These look a little tougher. Simplifying by factoring and using identities. Simplify the following trig expressions to a power of a single trig function. Here's what I want to do first. I want to remember that we had some really, really important trig identities last week. That tells me wherever I see sine squared theta plus cosine squared theta, I can replace it with a 1. Boy, would I love to use that. Replace all of that with a 1. And then remember, I said, don't memorize, think of it this way. What happens to this formula if I divide everything by sine squared theta? Well, sine squared theta divided by sine squared theta would be 1. Cosine squared theta over sine squared theta. What's that? Cosine over sine? Cotangent. And what's 1 over sine squared theta? Cosecant squared theta. So now I've got another identity. And remember, well, there's another one. If I just divide everything by cosine squared theta. Sine divided by cosine squared theta is what? Tangent squared theta. Cosine squared theta divided by cosine squared theta? 1 over cosine squared theta? Secant squared theta. I just keep all of those in the back of my mind. Because if I run across something that says cosecant squared theta minus 1, I should go, oh, wait a minute. Isn't that cotangent squared theta? If I subtract this 1 over here, can't I replace that with that? Because that'll help us make our equations easier, our expressions easier. So they gave us a huge hint here, and we're not always going to get huge hints like this. They said by factoring and using identities. So I look at A, and I think, well, there's sine of x all over the place in that one. I can factor out a sine of x. Let's see, that'll leave me with sine squared x plus cosine squared x. Oh, we like that. Because what is this?
1.
Talk about simplifying. Yes, like that. B. That's already in factored form, so that's a hint that maybe we should multiply it together and see what happens. It's already in factored form. This would be secant squared x. Hey, they're conjugates. Going to be no middle term. Last times last minus 1. Secant squared x, wait a second. Secant squared x minus 1. What would it be? Tangent squared x. Simplify the following to a power of a single trig function. Cool, got it. Oh my. Well, I think, well, what do I want to try? Well, first off, why are they giving me 1 over cosine theta? What's 1 over cosine theta? Secant. Secant theta minus 1. Okay, then I've got cosine squared theta. That one's all right. Secant. Got a negative in there. Can we drop the negative with secant? Yeah, cosine is even, and that's a reciprocal. So it's just going to be secant of theta plus 1 over cosecant squared theta. That's it? It's sine squared theta? It is. And I see something I really, really like in those parentheses. Do you see it?
Squared plus sine squared.
Cosine squared theta plus sine squared theta is 1. That looks familiar. We just did that. There it is. So if you're looking at something, you're saying, that is way too complex. They're trying to hide something from it by making it complex. Go back, figure out what do you have. Why are they writing that as 1 over cosine theta? We know that's secant theta. Well, they're probably trying to hide something. So see what happens when you replace it. Simplify by expanding and using identities. Well, we've sure seen this enough. Again, I don't like that they write all of this horizontally. You can see it much easier when it's a fraction. But, you know, we already said, hey, you multiply this together, you're going to get secant squared x minus 1 over sine squared x. And then we said, well, secant squared x minus 1, if we go back up to our identities, which because I'm recording, it's making me do this super, super slow. We'd subtract 1 and we'd get tangent. So that's going to be tangent squared x. Or sine squared x. Now I think to myself, can I take this further with something I know about tangent? Is there something about tangent that I know that has sine in it? Very good. Sine over cosine is tangent. So this would be sine squared x over cosine squared x as a fraction divided by sine squared x. Well, we don't divide fractions, we multiply by the reciprocal. Something good happens. So we notice sine squared x, gone. 1 over cosine squared x. 1 over cosine is what? Secant squared x. Oh, that's about simplifying. No? Got it. Single power of a trig function. Simplifying by combining fractions and using identities. Yeah, fractions are tricky because sometimes you're going to see what you need to see by putting the fractions together. Sometimes it's breaking them apart that actually helps you. But I look at D and I think, isn't this something that would be working from our Pythagorean identities up there? If you took 1 and you subtracted sine squared x, what would you get? Cosine squared x. And how about cosecant squared x minus 1? What will that do for you? Cotangent? Well, maybe this is a lot like the problem we just did. Maybe if we break this stuff up, we'll be able to see, hey, we're going to divide by something that's going to cancel things out here. So we've got cosine squared x over cotangent. What is that? Cosine over sine. Well, again, it's a fraction. We don't divide fractions, we multiply by the reciprocal. Cosine squared x is going to cancel right out. There it is. So again, think, how could I make this more basic as I go through it? E. We have two separated fractions. Now, like I said, chances are good that putting this together will give us something that'll help us out. So I'm just going to give it a try, but these are fractions. What do you have to have if you want to add and subtract fractions? Yeah, do. So this could get a little messy. We're going to have to multiply this one by cosine x on the top and the bottom, and this one by 1 minus sine of x on the top and the bottom. And that worries me a little. Here's why. We might lose track of this negative. So it's never a bad plan to change this to adding a negative so that you don't forget to distribute that negative as you go through it. So on the top now I'll have cosine squared x over cosine x times 1 minus sine of x. Now I'm not going to put that together just yet. I'm not going to distribute cosine x. My hope is something nice is going to happen and things are going to drop out. Plus, well, this would be a negative sine x plus sine squared x over cosine x times 1 minus sine of x. Well, now I have a common denominator. I can go ahead and put them together. Cosine squared x minus sine of x plus sine squared x over cosine x times 1 minus sine of x. What do you see? There's a 1 on the top. Cosine squared x plus sine squared x. Put those together and get a 1. Now what do you see? One minus sine x is going to cancel, right? How do we write 1 over the cosine of x as a single trig function? Secant. There it is. So those Pythagorean identities, constantly watching for them, thinking something to help me here. Come on, identities, give me something. Oh my. Ugh, look at that. Hey, I think that was one of our cofunction identities, though, was it? Tangent of pi over 2 minus beta. What's that supposed to be? Look back if you need to. Cotangent. Oh, let's do this step while we're there too. Cosecant. Negative disappears or not? Cosecant. Doesn't disappear. But let's think about moving it out front. Would that be an advantage if we could move this extra negative up front? Well, we'll have two negatives and that'll make it a positive. That'll work out nice. Cotangent squared beta plus, wait a minute. Cotangent squared beta plus 1. Check your Pythagorean identities. Doesn't that equal something? Cotangent squared beta plus 1 equals what? Cotangent squared beta. So these two negatives will make a positive. Oh, 90 degrees minus.
No, on the bottom.
Oh, I'm sorry, I wrote cotangent down again. Thank you. I think I meant to leave this one here. Thank you. Yeah. There we go. All right, so we take the two negatives out. And investigate again. See anything helpful? Can we cancel a cosecant? There's one on the top, there's two on the bottom. Yeah, and if you're thinking, well, can we? There's no plus or minus in this. Remember, canceling is a form of division. This is multiplication, so we can cancel one of these out. So we'll have cotangent beta over cosecant of beta. If we want a single trig function, I think we're going to have to think of primary functions, and that would be sine, cosine, and tangent. Cotangent is what? In terms of the primary three. Cosine over sine. How about cosecant? 1 over sine. Okay, well these are fractions. We multiply by the reciprocal, so cosine of beta, sine of beta, sine of beta over 1. Oh, looky, there it is. Cosine of beta. So multiple steps to get us there. And if you're thinking, boy, I'd really like to do 2 steps at once. Remember, when you're doing this on the test, it needs to be obvious to whoever is grading your test that you know exactly what you're doing. And so you need to show us that stuff step by step as you go through it. And no wonder I put it down here so I could have more room. That was a lot of stuff right there. So far, so good?
I don't have that
Oh
one.
no, this is the exact same one. I had just scooted it down in case I ran out of room. I did run out of room, but I kind of squished it in there anyway. All right, so far, I mean, if we just stopped with the Pythagorean identities and what we're doing right now, 4, 3, 2, 1, 0, we how you feel about improving those things. Yeah, it's gonna be touch and go for a little while. All right, so we're gonna keep using this stuff so that we get used to it. as we go through and we start solving trigonometric equations. So we're going to use some of this to do what we need to do. Solving trigonometric equations, we want to simplify expressions and or rewrite them in a more useful equivalent expression, which is what we just got done doing. It's very helpful when trying to solve trigonometric equations, algebraic, trying to find all the solutions. So solving a trigonometric equation, it says find all the values of x just in an interval from 0 to 2 pi. So we're not trying to give them all the answers that are out there. And we want to solve cosine cubed x over sine x equals cotangent of x. Before I even get started, this one has a restriction on the domain. And that's because we're dividing. And we know we can't divide by 0. So my restriction in the domain has to be that the sine of x cannot be 0. And I look at that right away, just in case when I'm doing the math, something comes up that says the sine of x equals 0, I can say that's undefined right away. We can't divide by that. So this looks a lot like a proportion. A lot like a proportion. And we're supposed to solve these algebraically, so I think I'm going to slap a 1 under there. And I'll just cross multiply. So cosine cubed x equals sine of x cotangent of x. Well, when we solve an algebra, we try to set it equal to 0 and find the zeros. I'll give that a try. Let me subtract this from both sides. Okay. Looks like so. Now, as we go through this, we try to figure out how can we use what we already know to get this. Well, we did our cross multiplying, and now we look and say, is this something that we could factor? No, but it's got a cotangent in there. That kind of drives me bonkers because this is a primary trig function and this is a primary trig function. So let's see what happens. You know what? Did we change this one to cosine on your packet? This is a little tough for today yet. You didn't change it? All right, then let's go for it. So give me cotangent again. What's cotangent? Does that help? Because the sine of x is going to cancel out. Maybe we just talked about changing that to cosine of x. Now can we factor? Take the cosine of x out of there. Cosine squared x minus 1. That sounds a lot like something we had a Pythagorean identity. Cosine squared x minus 1. You hear people flipping back. It's like that, right? So if we wanted to get cosine squared x minus 1, could we make it happen with what we have up there? If we multiply by -1, we can reverse that. So this would be cosine of x times negative sine squared x equals 0. So now we have this factored. Hopefully, if we think like a quadratic back in algebra, we realize, well, if this is 0, then the whole thing is going to be 0. If this is 0, then the whole thing will be 0. So our solutions will come from when does the cosine of x equal 0, and when does negative sine squared x equal 0. I'm going to go after the blue one first. First, we divide both sides by negative 1 and get sine squared x equals 0. Then we take the square root of both sides. And there is no such thing as plus or minus 0. So it says the sine of x equals 0. Wait a minute. Go back up to the beginning of this problem. Can sine of x equal 0 for this problem? So this one's undefined. So that means all of our answers are going to come from the green. All of our answers are going to come from the green. So I start thinking, where is cosine equals 0? And I make my little quadrantal sketch. It's always cosine then sine. Well, up here, we'd have 0, 1. Cosine would be 0 there, so that's going to be pi over 2. Down here, would be 0, negative 1. So that's going to be 3 pi over 2. Is there anywhere else, as we make our way all the way around, where cosine is going to be 0? So we found the solutions. Because it didn't say find all of them, it said find the solutions from 0 to 2 pi. And that's what we just did. From 0 to 2 pi, we have those solutions. It's pi over 2, and it's 3 pi over 2. So using the identities along with what we know about algebra, get those pieces in there. This one is the same thing. It says find all the values of x in just one rotation, 0 to 2 pi. 2 sine squared x plus sine of x equals 1. Well, last time we needed it to equal 0, so we could find it just like we did in algebra. So let's give that a try. 2 sine squared x plus sine x minus 1 equals 0. Well, if it's a quadratic in algebra, we factor. I don't suppose that's factor, is it? Let's try it this way. Let's pretend for a second that the sine of x equals y. Let's take out the sine of x so we're a little more comfortable with it. Is 2y squared plus y minus 1, is that factorable? We'd have to have a 2y. The other one would have to be y. We need two numbers that multiply to negative 1, and somehow, through FOIL, would give us positive 1. Well, if we put the negative 1 here, and the positive 1 there, outside times outside will be 2y, inside times inside will be negative 1y. We've got it. Is this more comfortable? For most people, yes. So if you want to substitute until you can get it the way that you want to see it, then do it. But we have to remember, that's not the problem we're working on. We need to put that sine of x back in there so we can solve this. So 2 sine of x minus 1 times sine of x plus 1 equals 0. Do you have to substitute? No. If you were able to factor this, keeping that sine of x in there, more power to you. But a lot of people get really overwhelmed when you first start working with trig and you're putting quadratic information in with trig. So if you need to, substitute. All right, so here's what we know. If this is 0, we're going to get a 0. If this is 0, we're going to get a 0. Let's set them up. Okay, we want to work backwards. We want to say sine of something, and then we'll use what we know about our unit circle to get them some answers. So, I guess I'll add 1 to both sides and divide by 2. Oh, wait a minute, that makes sense. Because we know of places where the sine of x is going to be 1/2. And then this one, we'd have to subtract a 1 from both sides. Sine of x equals -1. That sounds like a quadrantal to me. All right. So going back to the sine of x equals 1/2, I start thinking, I know that comes from my 30, 60, 90. So I need to figure out whether or not I'm talking about the 30-degree angle or the 60-degree angle. If you're a memorizer, you already have this done. But sine, opposite over hypotenuse, that would be 30 degrees. So that's going to be pi over 6. So the next thing I have to do is ask myself, since this is a positive 1/2, does that work? We already know there's going to be at least 2 spots as you go around the unit circle that are going to give you that for the answer. Well, it's positive in quadrant 1. So yeah, pi over 6 is a good answer. It's also positive in another quadrant. Sine is positive over here in the second quadrant. So if we put our little pi over 6 over here, what would be the correct label for that? 5 pi over 6. Any chance we could find a sine of x as a positive 1/2 in quadrants 3 and 4? So we're not even going to look there. We know that. These are the 2 we needed. Sine of x equals -1 screams quadrantal. It really does. So you start thinking, okay, well this is 1, 0, so there's a positive 1. Oh, back here, -1, 0. Well, that's 0 though. And you just kind of work your way around until you find it. And there's our 3 pi over 2. Any other quadrantals that would have -1 as their sign? No. So when we see 0 and -1, we really should be thinking quadrantal angles as we go through there. But we're also looking at our 30, 60, 90s, thinking, okay, if it's got a square root of 3, it's got to be in the 30, 60, 90. If it has a 1/2, in the 30, 60, 90. Square root of 2 over 2, that's going to be in the 45, 45, 90. And then thinking through which of these quadrants are positive and which are negative so we can get our solutions. So this again was just 0 to 2 pi. We're not finding them all. We're just saying in this interval from 0 to 2 pi. So now this looks very familiar. Didn't we just do this? What's different? All solutions. So we did do it. We just didn't find them all. We found the ones between 0 and 2 pi. But we also know that if pi over 6 is a solution, and they say all, anytime we go all the way around and we land right there again, we have another solution. So we'd have to say pi over 6 plus, and here's where we get into the, how do we know when to use 1 pi versus 2 pi? Let me show you. If I put 5 pi over 6 on here, they are not pi units apart. And how I know that is because 1 pi is a straight angle. So if I put these 2 on here, I know I'm going to have to use 2 pi n. But if I put them on and this happens, notice this is a straight line from those 2 terminal sides. Then I can get away with plus 1 pi n instead of 2 pi. So what I have to think of as I'm looking at these points for these angles is, Are any of those gonna line up perfectly straight if I draw them? And the answer for this one is no, they're not. So we're not gonna be able to combine any of these. We're just gonna have to say pi over 6 plus 2 pi n, and set of all integers, 5 pi over 6 plus 2 pi n, and set of all integers, 3 pi over 2 plus 2 pi n, and is the set of all integers. So only if we can see something in the picture that shows us, hey, these are completely lined up by 1 pi. If I rotate by 1 pi, then I won't need all this stuff. Otherwise, it's 2 pi n land, where n is the set of all integers. We don't have a choice. All right. I'm going to 4, 3, 2, 1, 0 you one more time. Because if you're comfortable with this, I can get everybody out there with it. I don't remember seeing a lot of real comfortable numbers. Yeah, let's do a few of these together. Huh? Let's do that. All right, away we go. Rapid fire. No, we're not going to be doing these as quickly as we possibly can. It's just more important that we're accurate at this point, so you're feeling comfortable. Take a look at A. What does your algebra intuition tell you would be a good thing to do? Then what? Right? Okay. You've seen that somewhere before, right? Which triangle? So what angle, give it to me in degrees, are we talking about if the sine is supposed to come out to the square root of 3 over 2? In degrees. 60 degrees. Okay, so we're looking at 60 degrees. What's that in radians? Pi over 3. All right. But we need a negative. So which quadrants are we looking at? 3 and 4. So we want to get the formal names for these angles, which means we're looking at this is 0. What would pi over 3 be? In the third quadrant. 4 pi over 3. Because you have 1 pi. Remember that straight angle is 1 pi. That'd be 3 pi over 3. 3 pi over 3 plus 1 pi over 3 would be 4 pi over 3. How about that little bad boy? It would be, because all the way around would be 6 pi over 3, because that would be 2 pi. So we're going to get 5 pi over 3. Now, do we need to put the plus 2 pi n and the set of all integers on this one? Why not? Here we go. Once around. So we're constantly thinking when we get to the end, is this it? Or should I be putting the 2 pi n stuff on there? What are we going to see that's going to tell us to put the 2 pi n information on there? Or all, find all the solutions. That's not what this said. All right, let me get my scratching out of the way here so we can do that one. Algebra instinct says to do what? Divide. Now secant. I don't like working with secant. What could I do so that that's not going to be secant anymore? 1 over cosine. Well, hey, if we're taking reciprocals over here, we just take reciprocals on the other side. Or you could cross multiply too. You could throw one underneath here and get the same thing. Cosine squared x times 2 equals 1. We're not done though, because that doesn't say cosine x, does it? It says cosine squared. How are we going to get rid of that? Square root. Hey, if we write square root down, don't we have to put plus or minus? And that'll be square root of 2 over 2. If we rationalize the denominator, which we know we're supposed to do, pardon my frogs, because this is a special one, right? Square root of 2 over 2 for cosine. Where did that show up? Where have we seen that? Square root of 2 over 2. Give me a special triangle. And really, we're going to think of it as 1 over the square root of 2.
Do you have to change it to cosine?
No, if you use secant, and
Okay.
you could keep going and take the square root. It's just most people learned this with SOHCAHTOA, and it's easier to think in terms of those primary 3 tree functions. So 45 degrees is what in radians? Pi over 4. But we've got plus or minus. So that means all 4 quadrants where we have a pi over 4 is going to be a solution. So pi over 4 in the first quadrant. Think about putting it over here. What should we label it in second quadrant? 3 pi over 4. How about third quadrant? 5 pi over 4. Fourth quadrant, 7 pi over 4. And again, it said from 0 to 2 pi. So we had 4 solutions for this one. Okay. How about C? Algebra instincts. What are you doing? Well, for people that gave me really small numbers, you certainly look like you're just doing this problem on your own now. What are you doing when you get there? Square root. If you're going to take the square root, what do you have to slap over on the right-hand side? Yep. Square root of 3 over 2. I think we saw that a whole lot. In degrees, what's going to give us a cosine of square root of 3 over 2? 30 degrees, pi over 6. Can we do it without drawing? Can you give me the other ones?
5 pi over 6.
Third quadrant. Fourth quadrant. Yeah. So you kind of think your way through putting that pi over 6 in each of those quadrants and going through. Okay, how about this? Ooh, really close, right? 2 minutes? Okay, so this one is a little loopy, so that'll be a good place for us to start tomorrow. But We're gonna mix those two things together. We're gonna use identities and solving at the same time. You'll be able to finish 5-1 day 1 and maybe get a little start on 5-1 day 2. Oh, actually, you'll be able to do 5-1 day 2 because it said if you got through A through C on the second day, you'd be okay. So let me scoop this up a little bit. So things to try. And tomorrow, definitely unique. I hope you check the schedule. The good news is we don't have any quizzes or tests in here this week. It's just that we're gonna make our way through our ability to go watch the girls play at state, the girls basketball. But I think we'll be okay. Because looking at the lesson, we don't have a ton of this left. So we should be all right. And I know they said if they win tomorrow when they play again. Is it Friday already? Or Saturday? Thursday? Oh goodness. Okay, well maybe it'll be a night game. Because they're gonna win.
It's a night.
Cool. They're gonna win.